Okay, so we all know where we're at? We're ready to go? Okay. So, there's something called tonicity. T-O-N-I-C-I-T-Y. Tonicity. So this describes the relative concentration of solutes into solutions. So when you're comparing, I'm just going to open it. We're going to be comparing solutions to each other. Or say, like in our experiment, we're going to compare the egg, what's in the egg, like as a solution, right? Because there's like fluids inside the egg, compared to the fluids that is going to be around it. So we're always going to compare solutions. And we're going to compare what's one thing inside of another solution. So like this, the starch was a solution, and the iodine mixture was a solution, so we can compare them. So tonicity is comparing solutions. To predict the direction in which a net movement of water will occur, the solution concentration must be compared. So when water is diffusing, what are we still talking about? Specifically the movement of water. Osmosis, yeah. Okay, so just a reminder, we're specifically talking about osmosis, on which I saw in your lab reports, you guys accurately said that that was diffusion, right? Because that was the movement of iodine, we could tell specifically. Okay, now, hypertonic, so a solution that is said to be hypertonic. So look at this root word, tonic, tonic. So that's where that's coming from. Okay, so hyper means like over the top, too much. Okay, the concentration of the solutes outside is higher than inside the cell. So when I think high concentration of solutes, I think, okay, a solute, remember that's what's dissolved in the solvent. So I think like too much sugar. When you have too much sugar, you're hyper, you know? So that's how I remember that word. So therefore, if the cell is put into this solution, water will leave the cell. Now, this can happen with either animal cells or plant cells. Now there's a very specific term for when this occurs in plant cells or animal cells. So when it happens in plants, it's called plasmolysis. Is the shrinking of plant cells in a hypertonic solution. And crenation, C-R-E-N-A-T-I-O-N, is the shrinking of animal cells.
I didn't know my hypothesis wrong.
Pardon me?
I didn't know my hypothesis wrong on the lab.
It's okay. That's just a part of science. Yeah, exactly. Yeah, a hypothesis is what you thought. What you thought cannot be wrong, because that's what you thought. It's just your thinking. It's okay. All right, so now, what does this even look like? So, what I want you to do is when we draw these, so hypertonic. So let's say let's draw a beaker, and we put a cell inside. So you always start when you're drawing these types of solutions, and to figure out where the water's going to go, is draw a beaker and a cell. Now what you think is, where is the water going to go? Okay, where is the water going to go? So we're told in a hypertonic solution, the concentration of solutes outside is higher than inside. So what I do is I write high solute kind of in my beaker, or you can maybe, let's put an arrow to our beaker. So in our beaker is high solute. So now when you think of a solution, it's made of solute, and we'll assume the solvent is always water. Okay? So if you have high solute, you'll have what water? High or low? Low. Okay? So you kind of make that statement first. We have high solute, low water. So then, remember, these words are comparing two solutions. So it's comparing the solution that's in here to the cell. So these will always be the opposite. Whatever the solution is, the cell is the opposite for hypo and hyper. So inside the cell then would be what amount of solute and what water? Low solute and high water.
So are we talking about like the same solute as outside?
No, we're this green, the green.
What would the solute be?
We could just say, let's say it's sugar.
So then it would be sugar for both of them?
Yeah, there is sugar in this solution, but there might also be sugar in the cell. But there's way, way more in the solution than in the cell. So then what you do, once you've set that up, you look at just the water. So I would put like a box around the waters. Because we're talking about where is the water going to go. Now, according to our definition of osmosis, water flows from what concentration to what concentration? High to low. So then you look here. Okay, here's the high, here's the low. So where will the water want to go from? From the cell to the solution. So that's how we can conclude where the water goes. So water diffuses out of cell into solution.
It diffuses?
Yes, because the definition of diffusion is going from high concentration to low concentration. We just know that water diffusing is osmosis. But osmosis isn't really a verb. We can't say it's osmosising. You know what I mean? Osmosis is a type of diffusion, it's not a verb. Okay. Okay, next I actually want to do, let's actually skip iso and we'll do hypo first and then I'll do iso last. Okay, so yeah, I'll do isotonic last. It'll be better this way. So hypo means under, so less. The concentration of the solutes outside is lower than inside the cell. Therefore, if a cell is put into this solution, water will enter the cell. So again, let's draw a beaker with a cell. So it says for hypo, the concentration of solutes is lower than inside. So we say low solute. So that must mean high water. Yeah.
Would they always be opposite?
Yeah. Now I'll give you, in a worksheet that you'll get today, some of them, this might give you, say, 25% solute. So how much water must there be then? 75? 25 is a lower number than 75, right? Yeah. So if it gives you numbers, you still make this kind of comparison, Okay?
Whatever these is.
Yes, that's isotonic. I'll show you that after this. Yeah. So now in the cell, then, since it's hypotonic, it will be the opposite. So this then has high solute and low water. Because this definition is based on comparing it to the cell. That's why we can assume it's the opposite. So now again, like last time, let's look at just our waters. So now we know, okay, water goes from a high concentration to a low concentration. So now water will go into the cell. So water diffuses into the cell. So the result will be a bigger cell. It'll expand because water's gone into it. And with a hyper, it will shrink because water has left it. So, and I think you guys have this diagram in your notes, right? Yeah. So you can see, and these are plant cells, and these are animal cells. So, look at this. Okay, so this is hypertonic. So we know when an animal cell goes through hypertonic, that was called crenation. And it shrivels up. And look at how the cell membrane, it just kind of like, it all shrivels. Now look at the plant cell. It's plasmolized because it went through plasmolysis. Look at how small the vacuole is. That's the vacuole. It's all shrunk up, so that's the vacuole, because that was the place where water was stored. And in hypertonic, then it leaves. So now, look at this. This part here, that's the cell wall. I mean, cell membrane. Cell membrane.
What's the cell membrane in the wall?
Just an open space. And here, that's the cell wall. So see how the cell wall, even though the plant cell has lost so much water, it's still remaining much more intact than the animal cell. So that wall provides that strength so that it still stays somewhat intact. But it has reduced, like if we compare it to, say, this one, it still has kind of caved in a little bit. And that's when plants will wilt. Okay? So yeah, this happens if plasmolysis gets too aggressive. The cell membrane will like tear off of the cell wall, and it could like get so bad that it would they can't recover. But generally, if you water a plant soon enough, or if the plant gets water, then it will recover. So then here, look, we see with the animal cell, when it gets lots of water, we got a good vacuole here. I kind of butchered that. Okay? And we say that it's turgid when it's full. And it's nice and big. Now, a plant cell can take in lots of water, and the cell wall again provides so much strength that it won't burst. But see, as you see with this animal cell, if it gets too big, it can blow up because it doesn't have that cell wall to give it that good structure. Okay? So we see that animal cells are a lot more susceptible to dehydration and overhydration. Okay? And then in the middle here, this will be the last one we talk about, is isotonic. So this is like everything's happy, everything's kind of balanced.
So would an egg be an animal or a plant?
Animal. Yeah. So we've taken off of the shell, And what is going to be left of your egg is the cell membrane is still around it.
Oh, we
Yeah.
took off the shell?
With the vinegar. The vinegar dissolved it. So we didn't cook it. We just, because then it would change the proteins if we cooked it.
Probably.
So the vinegar just dissolved it. It's cool when you see it. The shell's completely gone.
So.
So
Put a flashlight up here, you can see it too.
cool. You should do that. Okay.
Video, Josh.
Okay, so let's rewind and let's do isotonic. So, iso means equal. Oh, I tell you another memory tip before I go on. When I think of hypotonic, I think it has an O, so hypo, I think hippo, it gets big and fat. Like a hippopotamus is big, or an O is like big, round, so hippo gets big. Okay, so that's how I remember which one. And then hyper, it's like, oh, I've got too much sugar, right? So it's in a solution with too much sugar. Okay, and then iso is equal. So the concentration of the solute outside the cell is equal to the inside of cell. Therefore, if the cell is put into the solution, there is no net movement of water molecules, just odd molecules moving in and out. So it's like saying as many water molecules that go in are the same amount that go out. There's still some going in and out, but it's not like a whole bunch rushes in. So how do we show a isotonic? So here, let's have our beaker, and here's our cell. Now, because I'm not doing because the comparison is going to be equal, I'm actually going to use numerical values for this one. So let's say in the solution, we say is 10% solute. So that must mean that we have 90% water. If this is isotonic, we'd have the exact same thing in our cells. 10% solute and 90% water. So it doesn't always mean that it's 50-50. It means that the solution is the exact same as the cell. So then there's no high to low concentration of water. So these are equal. So the same amount of water that goes in is the same amount that comes out. So water is still moving, but the same amount that goes in is the same amount that comes out.